Hello everyone. In this video we're going to be solving a nice logarithmic equation with natural log, which is ln. So ln is the log with base e, which is Euler's number. Let's go ahead and take a look at this equation. We have ln of 1 over x equals 1 over ln x. Now I didn't use parentheses around the argument here. Hopefully it's understood, but it's meant to be that way. Okay? So we have this equation. How can we solve it? Well, it kind of looks like an identity, doesn't it? Like, wouldn't it be nice if we had an identity like this? But this is not a general rule. It is specific for this x. Let's go ahead and talk about some rules, though. Properties of logarithms or rules are actually very helpful. Knowing the definition of logs is also very helpful. So let's go ahead and talk about some rules, such as this one. If you have the log or ln of a quotient, then you can basically write it as the difference of two logs or ln's. If you have the ln of a power, then it's just that power times the ln of the number without the power. So you can basically bring this n to the front, and we use this a lot. You've probably seen my previous videos. Hopefully, if you didn't, please check them out. Anyways, you can just move the power to the front. And then particularly if n is equal to -1, which is something we're going to use here, when you have something like ln a to the power -1, then you're going to move the -1 to the front, and that's going to become negative ln a. In other words, ln 1 over a and ln a are opposites. So you can safely say that, hey, ln 1 over a plus ln a is equal to 0. But of course, a should not be 0 in this case. We have a requirement if x is real. If this function is defined over real numbers, then x needs to be greater than 0. Okay? Cool. So under these conditions, we can go ahead and simplify this equation. Let's go ahead and write the original problem one more time. We have ln 1 over x equals 1 over ln x. And ln 1 over x is going to be written as negative ln x from the property we just talked about. And then this is going to equal 1 over ln x. And obviously, cross multiplication is going to follow, right? If you multiply, you're going to get negative ln x times ln x equals 1. And it just means the negative of ln x. Notice that this negative stays outside the parentheses because it's there. It's kind of like the difference between, like when we write something like negative 5 squared and negative 5 squared in parentheses. Obviously, these two things are different, right? So that equals 1, and then you can multiply or divide both sides by -1, and that's going to give you something very interesting. What is that thing? Well, something squared equals -1. And we just recently talked about it. If you haven't checked out my new channel yet, which is called aplusbi, so go ahead and check that channel out. I talk about complex numbers. I started the lecture notes. I believe we've done the third one recently, and I'm going to try to upload a new episode every day so that we can finish the lectures and then go into the problem solving. Anyways, so if you've seen some of those videos, then you probably recognize this. ln x can be written as I or negative I. In other words, there are two numbers whose square equals -1, and those numbers are I and negative I, and I being an imaginary number here. Of course, it's not real, but it's used in real life in so many ways. Anyways, so the problem is, where do I go from here? Once I got ln x equals I, how am I going to solve for x? Well, that should be kind of straightforward, hopefully. If you think about it, the definition of log and the relationship between the exponential function and the ln function, they're inverses, right? And if you even check out their graph, ln x looks like this and e to the power x looks like that. And you're going to notice that they are actually symmetrical with respect to y equals x. That's what most, if not all, inverse functions do, right? Okay, great. So this is the graph of ln x, and this is e to the power x. Great. So we can go ahead and do the following then. We can just use the definition of logs or do the following. E to the power ln x is equal to x. So by doing e to the power both sides, ln x equals I implies x equals e to the power I. And then ln x equals negative I implies x equals e to the power negative I. Of course, e to the power negative I is just the reciprocal of e to the I. Whatever e to the I is, we can just reciprocate it. I don't know if that's a good word to use, but you get the idea. We just flip it. So the next question would be then, how do you simplify e to the I? Or do you want to leave it like that? Well, I don't think so, because e to the I is kind of like weird, like it's not well defined. Well, complex numbers aren't real anyways. They're not well defined. Maybe they're well defined, but in a different sense. Anyways, I talk too much. So e to the I needs to be simplified. You don't want I in the exponent, because what does it mean? Like raising something to the ith power? And I is supposed to be a constant, right? So we're going to simplify it. How do we simplify it? Of course, one of the greatest mathematicians, maybe, for me it's not maybe, for me he is the greatest, Euler. Euler's formula gives us an awesome opportunity. So Euler's formula goes like this: e to the power I theta equals cosine theta plus I times sine theta. Awesome. Theta is basically the angle, and again, in my lecture videos, please check them out. I go into more details. So using this formula, we can kind of try to understand what e to the I means. Now, when you take a look at this, how does e to the I relate to this? Think about it. And I notice, hopefully you notice too, that in order to evaluate e to the I just need to take theta equals 1. Simple, right? Because if theta is equal to 1, then this becomes e to the power I theta becomes e to the power I. Awesome. Then I just need to replace, because this is kind of like a function of theta, because the only variable here is theta. So if I change theta, I can change it on both sides. In other words, if theta equals 1, then this implies e to the power I equals cosine 1 plus I sine 1. One of the things you need to be careful about is 1 must be in radians. It's not 1 degrees, it's 1 radians. And how can you interpret that? Pi radians is 180 degrees, right? So 1 radian is going to be a little less than 1/3 of 180 degrees, which is probably something like 57 degrees maybe. Make sense? Okay, that's about it. Now, what is cosine 1 and sine 1 though? I'm going to show you the numerical values in a little bit. So this is one of the values of x, okay? The other value is going to be the negative of that, and when you find the negative, you're just going to replace I with negative I, right? Something like, or I should say theta becomes negative 1. And then if theta is negative 1, cosine is even, so it's going to be cosine of 1 again, but sine is going to change, and that's going to be my second x value. So we could call these x sub 1 and x sub 2. So those are going to be the x solutions, the values that we're looking for. And now let's go ahead and take a look at the results from Wolfram Alpha. Obviously, the solutions are not real. That's why the graphs do not intersect. There are 2 solutions, and those are the numerical values. And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and don't forget to check out aplusbi. Bye-bye.